Buonasera.
Good evening. Good evening, everybody. And good evening to all the people here in person and to all those who are following us from remote. This year's encounter will take us to one of the farthest places ever to be conceived. Well, it's very far in terms of distance. We're going to talk about a place that is at 30,000 light years from where we are. But it is also far, far, far away in terms of its functioning and how it works, how this place works and its surroundings work. Even space and time behave differently there from what we're used to, well, from the reality we're used to and familiar with. So we're talking about the supermassive black hole that was discovered at the center of our galaxy. The importance of this discovery is enormous, not just because that let us better investigate and know the evolution of our galaxy and the dynamics of our galaxy as well as of the other galaxies of the universe, but also because that let us check with a great deal of accuracy the ideas that we have about gravitation, because the gravitational force is the dominating force in the universe. So this discovery is really extremely important. It's so important that it was awarded with the Nobel Prize, and we have an exceptional sort of guide to tell us more about the path to this discovery. And this is a pathway that lasted 40 years, is the protagonist of this discovery, Reinhard Genzel, Nobel Prize winner in Physics 2020. Reinhard, thank you very much indeed for being with us tonight. Thank you.
Having me.
Reinhard is a director of infrared and submillimeter astronomy at Max Planck Institute for Extraterrestrial Physics in Garching, Munich, and is also professor at the Graduate School of University of California, Berkeley, where he is now, and is also honorary professor at Ludwig Maximilian University, always in Munich. Among his interests in astrophysics and, well, wide and deep, and that includes the study of active galactic nuclei that are strictly connected to another area of research of yours, so the supermassive black holes, but also the stellar formation, the evolution of galaxies, and experimental astronomy in millimetric, infrared, and sub-millimetric, so all the technologies relating to these studies. He was awarded with dozens of prizes, all prestigious, so really dozens, literally. The Sho Prize, the Crawford Prize, to name but a few, for astronomy, and in 2020, he was awarded the Nobel Prize together with Andrea Ghez, and the motivation stands for the discovery of a supermassive compact object at the center of our galaxy. So Reinhard, guide us along this journey, and thank you very much for being with us tonight.
Welcome, everyone, and good evening. Here it's noontime, but you have already a wonderful evening in Italy. So I want to invite you on a trip, a rather unusual trip, I have to say. I'm actually on that trip, and as you see, if you like, I'm unfortunately on my way to disappear pretty soon in a black hole. And I wanted to tell you about this trip of mine, which has lasted throughout my career as a physicist and astronomer, 40 years. And I'll tell you what we found. And you will see that this personal trip of mine is actually embedded in a very important story of the universe, but also of the theory of general relativity, which is now 100 years old. So I'll tell you about galaxies like our Milky Way and these weird things called black holes. So before we start with the sort of scientific part, I thought I invite you to a nice movie which was made a few years back, which shows you our Milky Way. You know, our Milky Way is something you have seen at night, perhaps, as sort of a band of light, stars, about 100 billion stars in our Milky Way, and we are in a plane. The Milky Way rotates and subtends a planar structure. There's also some gas and some dust. That's where, in fact, the new stars are forming. In our Milky Way nowadays, about 2 stars are forming every year. This used to be much more in the distant past when the Milky Way was forming, and I'll come to this particular story at the end of my talk. But let's just go ahead now and start our little trick. Okay, well, thank you for coming along on this trip, which started harmless and ended in the end in a black hole. It's actually a fairly realistic description of our Milky Way, the many stars in the center of our Milky Way, and then in the center of that, an object which you will hear about in this talk. Now, from a more general point of view, however, this story really is embedded in our attempt to understand the universe and how the universe evolved. And here, the theory of gravity is a very, very important part. And as many of you know, Albert Einstein, about 105 years ago, was the first to walk on this path. Many have followed, very famous physicists and mathematicians. Several Nobel Prizes were given. In fact, I shared, and Andrea, I guess we shared our Nobel Prize with the man in the middle of the picture, Roger Penrose, who is a very famous mathematician who's worked on these objects we now call black holes. And I'll try to explain to you a little more what these things are. They do emerge from the theory. But of course, the question in the sciences is always, do these things really exist as predicted by theory? And for that, it took a long time to find candidates. The first real candidates were discovered in the 1960s. That's when the radio astronomers started looking at the sky and mapping out the radio sky. And they found objects which were very, very bright. And when people then looked at their spectra, from that one could infer that they are also very distant, billions of light years away, extremely distant, and therefore we're looking sort of at the past there. A number of theorists then work on this phenomenon of these quasars, and by the early 1970s, basically everyone was sort of pretty certain that the only way to explain this enormously bright objects was if you have a massive black hole. Then you can have material fall into the black hole. Now, as you will see in about a minute, black holes, of course, are black because even light cannot escape. But that is only true within the so-called event horizon radius. Outside the event horizon radius, material can move and shine, and the gravitational energy, which is converted into heat and radiation, is what might make these quasars so bright. But then, of course, the question is, that's a nice hypothesis. How do we prove that these objects really exist? And that's the story which you will hear about. And it took another 50 years now to come to a point where several routes have suddenly opened up for us to study these objects as if they are laboratories. You'll hear the story of Andreas and mine about looking at the center of our Milky Way and showing that there is an object which convincingly looks like a black hole. A few years earlier, in fact, gravitational waves were discovered after a long, long period of very difficult work. And the first radiation from these gravitational waves came from two what we think are stellar black holes, inspiraling into a single black hole and emitting gravitational waves in the last 100 milliseconds of their path before this was all over. And finally, radio astronomers have begun to look at quasar-like objects and mapping them in the millimeter range and seeing, in fact, features there which are predicted by general relativity and might indeed have to be interpreted as black holes. So we are in a very important part of the evolution of this field, where things which were predicted 100 years ago are now actually verified and studied by the experimentalists and shown to be, in fact, correct. That's remarkable, these weird objects called black holes. So how could you see something which you can't see? So let's think of the sun. There's a sun, which we know and love. And if you imagine you had a rocket which you want to shoot from the surface of the sun into interstellar space, then to overcome the gravity of the sun, you have to have a velocity of the rocket of about 600 kilometers per second or more, or 690,000 kilometers per hour. So that's a very fast speed. But this is all dictated, of course, by the gravity of the sun at its surface. And the gravity depends, we know, on the mass. So if you have a heavier sun, then the escape speed of that rocket would have to be greater, but also on the size. So if the sun is smaller, then at the surface, the escape speed also increases. Now let's make an experiment in our thought, and let's shrink the sun from its current diameter to a size of only 3 kilometers. And then again, calculate what the speed of the rocket would have to be. And surprisingly, the speed comes out to be 300,000 kilometers per second. That's the speed of light. And we know from experiments which were already done at the end of the 19th century that the speed of light is the fastest communication which you can have. So make the sun even a millimeter smaller, then light cannot escape from within this region we call the event horizon, and which in the case of the sun would be about 3 kilometers. Okay, so now let's go a little further in this game and think about Kepler and Tycho Brahe, who back then in the 17th century, 16th century, mapped out our solar system. And they looked at the motions of the planets, and the planets move around the sun, as you well know, in circles or ellipses on stable orbits around the sun. And so, for a moment, of course, if we now think of a sun which doesn't shine anymore because we have turned it into a black hole, what would happen then? Well, the planets would still orbit the central object, the sun, in the same way as before. The radiation of the sun doesn't play any role there. It's just the mass of the sun. And if you then look at the motions of the planets, then we know these are dictated by the so-called Kepler's laws. The planets which are closer to the sun move faster, and the planets which are further away from the sun move slower. So if Tycho Brahe and Kepler would have analyzed another solar system which had a black hole in the center, but the same planets, they would have come to the same conclusion. There has to be an object in the center which has one solar mass. So that's how we can see what we cannot see. We use the effect gravity has on particles or on objects surrounding the object in order to then measure the mass and see whether it might be so concentrated that it has to be a black hole. Now, this experiment we cannot do with quasars because quasars are so far away, I said already, billions of light years away. So we have to have objects which are closer. And in fact, in 1971, two famous British theorists, Donald Lindell and Martin Rees, predicted, well, if these black holes, these massive black holes, exist in quasars, they might exist in other galaxies, including our own. And then we could perhaps see objects in their vicinity, gas clouds and stars. So that's how one can then experimentally try to verify whether such a black hole really exists. And indeed, if you look at the center of our Milky Way with modern telescopes in the infrared or in the radio region, you find a very dense inner region, which you also saw in the movie, with a lot of dust around it. So much dust, in fact, that we cannot see the center of our Milky Way in the visible with our eyes. But we can see it with somewhat longer wavelengths, the infrared eyes. So this is a modern picture you make with a big telescope of the central few light years surrounding the center of our Milky Way. And you see there are very, very many stars, dense star cluster, about 1 million times the density of the stellar environment we are in. So at night, so to speak, if you were in the galactic center, it would not be dark. So this star cluster is the object which is of interest, and the radio astronomers looking at the galactic center discovered a very compact source, which with modern technology we now know has a size of only 40 micro-arc seconds. I'll tell you a little more about these sizes later, but 40 micro-arc seconds is about the size of a euro coin on the moon. So it's a very compact object, and that might be, in fact, the possible location of where you might suspect a black hole. The next step was to actually use these traces, as I explained, to measure the mass in the center. And that was done first by a very famous physicist, Charles Townes, and his students. And I then actually joined as a postdoc here in Berkeley in the 1970s and 80s. And what Townes and his students did was to look at gas clouds in the vicinity of the radio source. In pink, you see ionized gas, so that's protons and electrons, a plasma, and the green is neutral gas. And they were basically using spectroscopy, so resolving the infrared light into different wavelengths, and then looking at line radiation of an atom, neon, and then looking at the Doppler shifts one can detect from these various gas clouds. And these Doppler shifts tell us how fast gases are moving. And so what they found was that the motions were extremely large, much larger than you would have expected from the stars themselves. There must be an additional mass, they concluded. And in fact, by the mid-80s, our group in Berkeley was pretty much convinced that this object of a few million times the mass of the sun in the center of the Milky Way might be such a black hole as predicted by general relativity. So the evidence for such a black hole is then shown on the left diagram there, where you basically plot the enclosed mass as a function of the distance from the center of the radio source. So right at the source, you're on the left side, and then you're going out. And you see that when you go very far out, the mass changes, increases. That's a sign for an extended mass, and that's basically the Milky Way itself and the nuclear star cluster. But when you come closer than about a few light years, the mass does not seem to change anymore. It remains at somewhere between 2 and 4 million solar masses, and that's evidence for a compact mass. Now, of course, the question then is, must it be a black hole? And that wasn't clear at that time. Plus, many of our colleagues felt the evidence we had through these dust clouds and gas clouds was, somewhat difficult to interpret, because there could be forces other than gravity. So we needed to go on and do two things. First of all, not measure the motions of gas clouds, but stars. Stars are really ideal probes of the gravitational potential. And we had to go in from the few light years region inside, because a few light years corresponds to about 1 million times the event horizon size of a few million solar mass black hole. So that's the description, so to speak, for our work, which was cut out for us in the next years. And we made progress all the time. And at all times, of course, technology played a very, very important role. At the time we started, for instance, there were no cameras in the infrared. Of course, CCD cameras is something you use every day, but in the infrared, that was really very difficult. But then, you know, over time, they were developed. The next thing is, if you have a telescope, and it might be a small telescope or a big one, and you look at a distant star, the radiation, the waves from the star have to go through the atmosphere, and the atmosphere is turbulent, and that means that the wavefronts get distorted, and the images therefore get unsharp. And the trick we are using is to measure the distortions and then correct for that with a so-called deformable mirror. And then what is initially, you know, a very disturbed, smudgy image can be made very sharp as the so-called diffraction limit of a telescope, which is proportional to the distance. So the bigger telescope you have, the sharper you can look. So that's the kind of technology we needed to develop. Of course, to make this correction, you need to actually have a star which is bright enough to analyze the wavefronts. Sometimes there is no star. The solution for that is we create our own stars. We create a star by shooting a laser into the upper atmosphere, and at a height of about 90 kilometers, there is a layer of a few kilometers where there is sodium atoms which originate from meteorites which hit the Earth every day and then basically fall down, and the meteorites are basically destroyed, and the atoms, a little bit of sodium in these meteorites, can be used to focus on them and basically generate an artificial laser star at the height of 90 kilometers, and that light then comes back to the telescope and can be analyzed. So like with the gravitational wave and many other things in modern science, technology is the key way to make progress. And certainly that was important for this work on black holes. So then we started observing, and in fact, by that time, a second group in California, Andrea Ghez and her colleagues also joined and started using their telescope. We used the telescopes of the European Southern Observatory, which are located in Chile. You'll see them a little later. And Andrea used the big Keck telescope on Mauna Kea to then basically make sharp images with this adaptive optics technique of the region around the radio source, Sagittarius A star, which I told you about. And on a scale of about a half arc second, which is this green circle, half arc second at the distance of the galactic center of 27,000 light years away, corresponds to about one light month. So at that scale, you can measure the motions of the stars over time, and that's in this picture shown as three colors from 3 different years. So red is year 1, green is year 2, and blue year 3. And you see there is one star very close to the radio source, which is marked by this green cross. This star obviously moves very, very fast, more than 3,000 kilometers per second. That's remarkable. That's much faster, of course, than the Earth around the Sun, about 100 times faster than the Earth around the Sun. And there are many such stars. And if you look more closely, you can see that the stars further out move less. The colors are not so obvious anymore. That's Kepler's laws in action, so to speak. That's exactly what we saw earlier. If there's a central mass, then the innermost objects, like the star very close to it, move much faster than the outer ones. So by the mid-90s, we had from both groups good statistical evidence that there must be a central mass of a few million solar masses. In fact, that's pretty much the same evidence we had a decade earlier with the gas clouds, but now closer in, and also with stars rather than with gas. So the evidence was much stronger. So must it be a black hole? It likely is, in fact, because now we are on a fairly small scale of a light month where we can make these statements. But actually, there are other possibilities you might think of. For instance, you could think of a cluster of neutron stars. There would be, could be very massive. A million neutron stars in this central region would have the same mass as a single few million solar mass object. And because neutron stars are relatively heavy, they might sink to the center. Stellar black holes also might be a possibility. So it's not clear that this has to be a black hole and a single black hole for that. So to know that, we have to still make better measurements. How could we do that? Well, you could make more precise measurement, and in particular, measure more than just statistical motions, like you see here. You just, over time, see the stars move in the sky. Takes a few years to do that, and then you have a statistical statement about the mass. What you really would like to see is a single star and follow its orbit when it moves around a black hole. And initially, that actually seemed like a very ill-founded idea, because the orbital timescales of possible orbits of stars on these scales are hundreds of years. So that's longer than even long-lived humans can hope for. But we were lucky, because nature gave us several stars which are much, much closer on solar system scales. Here is, in fact, our star, the star S2, which moved moderately fast. When we started, you see 92. That's when we started up there. Then it moved downwards toward the position of Sagittarius star, and then all of a sudden, in 2002, it was very, very close to Sagittarius star. Only a mere 17 light hours. 17 light hours. That's the distance between three to four times the orbital radius of Neptune, the planet Neptune. So we are really now on scales of the solar system, and then they moved back out. So it's clearly, obviously, on a highly elliptical orbit. And our measurements are the ones in blue, and the measurements from the Keck group in red. So we found the same thing, which is a star which had a 16-year orbital timescale and came as close as 17 light hours. So now you can go ahead again and infer now the mass inside the Perry distance. So that's the closest distance there, which it reached in spring 2002, and it moves there with about 7,000 kilometers per second. 7,000 kilometers per second. That's incredible. That was never ever seen before. And if you calculate the mass, which must be included, you end up with the same few million solar masses, which we knew before, but now within a very small volume. Now, even the physicists were beginning to accept that this is likely a black hole. But must it be one? Could it be not, possible that there are other options? Plus, in order to make the conclusion I just gave you, we applied general relativity. And do we know that general relativity would actually be correct in such an environment? General relativity has been tested numerous times in laboratories on Earth, in the solar system, but this is, if you like, the conservative, slow, universe. Here we are moving at almost relativistic speeds, and so the question is, can we possibly make measurements which test general relativity on these kinds of scales in the Galactic Center Laboratory? That seemed like an outrageous idea in 2002, but as you will see in a minute, it then was possible to realize it because we knew the star would come back in 2018 to pretty much the same position. And maybe then, 16 years later, we would have the technology to measure things so precisely that we could test general relativity. But many other things happened too. Many more stars were found and showed us how beautiful the universe is. So clearly, in the center of our Milky Way, there's a massive object. We know that now. It's surrounded by these stars we surely did not expect to see. And these stars are our test particles to test the gravitational potential. How can we make progress? Well, the European Southern Observatory by that time had on Paranal Mountain in Chile 4 8-meter telescopes installed, 4 8-meter telescopes. We had been using one of them so far, but in fact, there is the option of bringing the light together from these 4 telescopes with a technique we call interferometry. And so over the next 15, 14 years, we developed a very ambitious instrument which had never been built before. It was a European consortium from French, German, and Portuguese groups together with ESO in this wonderful European collaboration on Paranal Mountain to bring the light of these 4 telescopes together to a super telescope. The way this works is that if you have light waves coming into the atmosphere and you have 2 telescopes, then you can bring the light through an underlying tunnel system to a combined locus and then interfere the light. And when you do this, then you get information which is of the resolution of a virtual telescope of the separation of the telescopes, which in this case is 130 meters. So you get a resolution which is more than 10 times that of a single telescope. So that's how we proceeded, and that's what gave us absolutely incredible information in the last few years about this laboratory of astrophysics. So what can gravity do? Well, gravity can resolve a euro-cent coin on the moon. Okay, so that's about the event horizon size at 20,000 light years away of a 4 million solar mass black hole. So we can measure extremely precisely, and over time, ever better. So we started in the upper left with systems which were only seeing limited. Then we went to adaptive optics, as I described to you, where we improved the resolution on an 8-meter telescope by about a factor of 10. And now, in the bottom right, we have this imagery we can do with interferometry in the infrared, which is another factor of 15, 20 times better, such that we can see the motions in the lower left of stars immediately around the central points of Sagittarius A star. Now that's our terrific tool we have to test gravitational potential in the center. So these orbits, which we saw before, and we have about 50, 60 such orbits, and then we can go into the very center and with the interferometer follow the motion of the closest orbits. And it turns out the star S2, which you see here as a blue ellipse, May indeed came back in 2018, and then we were able to measure the motions every day. So when S2 moved inwards, it had its peri on the 19th of May 2018, and the red dots give you the positions on various days before and after this peri approach, when the star was only about 120 astronomical units. So an astronomical unit is the distance between the sun and the Earth. So 120 times that distance away from the black hole. And all of this with extremely precise methodology. And then this year, we saw another 3 stars going through similar spectacular peri distances. So we have extremely sensitive information on the gravitational potential. So the first thing we did in order to test general relativity is to check the effect predicted by general relativity, which is called gravitational redshift. Basically, when light is emanating from a source of strong gravity, then the clocks near the source go slower, and the radiation gets redshifted. So if you look at the motion of the blue star S2, but now in velocity space, then this is the curve, and when it goes through peri, then it goes from one side, from plus 4,000 to minus 2,000 kilometers per second in only a few months. And during that period, we can then look at the deviations of the Newton theory from general relativity. Newton, on this upper right diagram, is the horizontal gray line, and general relativity predicts this red line. So basically a shift into the red to longer wavelengths of the emission from a spectral line on the star, and that's the effect of the general relativity redshift, gravitational redshift, which you see in the movie on the lower left. So clearly, general relativity with this particular test fulfills the observations exceedingly well to only a few % accuracy. The next effect we were interested in observing is the so-called precession of the orbit. So if you have a star orbiting another star or a black hole, then in Newton theory, if there's nothing else around, then the orbit stays the same throughout the period of time. So the star comes always on the same orbit. That is not the case in general relativity. In general relativity, the orbit starts to precess in the plane of the orbit. That's called the Schwarzschild Procession. And for the star S2, that's a modest amount. It's about 12 arc minutes, 12 parts of a degree per orbit, and that's in fact can be seen as a deviation from Newton again in the lower right diagram, where the Newton orbit again is the gray line, and what general relativity is predicting is the red line, and you see the star moved on more or less a Kepler orbit when it was away from the black hole on the left side. But then near peri, that's when we started to observe with gravity, these cyan circles tell you the gravity measurements, and they basically show you how all of a sudden the orbit precesses, makes a kink, and follows general relativity. The star is now quite a bit away from the black hole, so we can actually see this precession directly in the upper right. The last time we made measurements, these are the open circles, and now this year we've been able to measure these closed circles, and you can clearly see that the orbit has shifted to the right by about half of a milliarc second. These are extremely difficult measurements to make, but it's not possible to do this. And again, general relativity is correct, and we can certainly say that given these measurements, it's extremely likely that the central object indeed is a black hole. Now, how can we go still closer to the central region? Well, on our images in the infrared, we do see Sagittarius star in the infrared as a variable source. And in fact, when we do so and measure very precisely when it's bright and has flares, we can see a motion. You see this in the upper left. Over about a period of 40 minutes from the red dots to the blue dots, very difficult measurement. You see there's a change in the position of Sagittarius star. And our interpretation is what we're seeing here are hot clouds of gas which emit synchrotron radiation, in which are very close to the event horizon on scales of about 10 times the event horizon scale, and moving with a speed of 30% the speed of light. This is very difficult stuff, and we need to still measure better, but it's clear that if this measurement is correct, well, then we have shown that the 4 million solar masses, which I've told you about, are contained within a few times the event horizon size, so clearly this must be a black hole. Likewise, the VLBI radio interferometry measurements at 3 and 1 millimeter also show us a very, very compact source on that scale. So I would say the stage really is now that in the case of the galactic center, we have shown beyond any reasonable doubt that there is a central mass of a few million, 4 million solar masses, and that this mass is really concentrated to a scale of that of a black hole. So when we were starting this experiment 4 decades ago, we were on the upper right side, and we're just seeing this constant mass, and we've worked our way inwards to the central region. In fact, we can now actually see that other than the black hole, there's very little else surrounding it. So we can set limits to any extended mass outside of the black hole and within the orbit of the stars. So that's extremely interesting measurements because it tells us, could there be a second black hole, for instance, or are there many stellar black holes, so to speak, drawn to the central region? So that's what we have after 4 decades. But that's just the galactic center. What about other galaxies? So now let's go and talk about galaxies and their evolution. We can take with big telescopes and also the space telescope images and also spectra of extremely distant galaxies, which were formed at only a few 100 million years after the Big Bang, can look at their motions, can look at their masses, etc. So we've seen that galaxies started forming about 500 million years after the Big Bang. Then they grew very rapidly into very big galaxies. Some transited in that development to so-called elliptical galaxies, and some, like our Milky Way, stayed disk galaxies. So we can see this, and we can also look, broadly speaking, at the evidence for quasars in them and see how that developed. In nearby galaxies, in fact, we can also measure the central masses, not as well and as decisively as in the galactic center, but for instance, in our neighboring galaxy, Andromeda, there is also a central object of about 100 million solar masses, so about 25 times larger than in the center of the Milky Way. And in fact, many people have been looking at nearby galaxies of various masses and find that the mass of the central object is somewhat proportional to the mass of the center of the galaxy. So as if the two were growing together in the early universe, the bigger the galaxy, the bigger the central black hole. And in fact, numerical simulations have very much confirmed this, and I'll show you in a second how we can think about this. So black holes and galaxies seem to be in a symbiotic relationship. And that happened in the early universe. So if we look back in time, the Big Bang was about 13.7 billion years ago. We are on the left side. If you look at the quasar density in red, then nowadays quasars are very rare. And about 10 billion years ago, about 2-3 billion years after the Big Bang, quasars were much, much more numerous. And at the same time, I mentioned this at the beginning of the talk, also the galaxies grew much more rapidly, about 20 times faster. So our Milky Way at that time formed 50 to 100 times the mass of the sun per year. So they were much more active objects because at that time the universe was more compact, had not expanded as much, and there was much more gas around. In fact, the most distant quasars we can nowadays see also were already there at about 800 million years after the Big Bang. We don't actually understand how they could have grown so rapidly. And so that's something which we want to study with still bigger telescopes in the next 20 years in space, but also on the ground. The European Southern Observatory is building just now the world's biggest telescope with a diameter of 40 meters. So this is an exciting period. So to show you how we can imagine all of this, I show you now, as at the end, a movie from a very, very sophisticated simulation in big supercomputers, which shows you how galaxies came to be in the presence of dark matter, formed in dark matter filaments, and then grew over time until their central black holes had grown to very large extents and started spewing out energy and explosions, which you will see in the movie, and in fact stopping the growth of galaxies. So you see, we have, through experimental work and simulations, now learned how galaxies evolved over cosmic time, and that black holes played a very important role in their evolution. So the question I've asked already several times, I want to ask at the end again, are we done? I've told you that we now think we have very good evidence for these black holes, but there are still some great mysteries. One mystery is the theory of general relativity predicts that all the mass of a black hole is in a central, infinitely small singularity. And that we physicists don't believe. We believe that there must be an extension, an upgrade, so to speak, of the theory to explain how gravity works on the smallest quantum scales, and that this quantum theory of general relativity might change a number of things. One would be, in fact, the central singularity might go away and be smeared out some. The other one is that information which seems to get lost as you have black holes grow might still be conserved and in fact might be accessible to measurement. In 20 years from now, the European Space Agency is hoping to launch a very ambitious space experiment called LISA. LISA consists of 3 satellites which are connected through laser beams which are sent from one to the other. And these laser beams are used to sense gravitational waves on very large scales. And that's the way to test the gravitation on very, very small scales around big black holes. And in fact, thereby observe, for instance, the in-spiral of a stellar black hole into a million solar mass massive black hole. And that is the way we think when 20 years from now we can understand and test the physics just at the event horizon and maybe learn about these quantum effects. And then we will hear the following. At the end is silence, and that's the silence of the black holes. Thank you.
Grazie, Reinhard.
Thank you. Thank you, Reinhard. Thank you. I don't know if you were able to hear the huge round of applause and the gratitude for this wonderful, magical journey. I'd like to ask you 2 quick questions. A couple of more general questions in relation to the journey you guided us through. So 40 years of studies, of technological innovation, of genius ideas brought you to this discovery. Clearly, there are technical capabilities that are very specific and that are indispensable for such a discovery and such a work. But there are also human qualities that play a very important role when it comes to such a wide collaboration and such a long one, and certainly being strong-willed and determined, the sort of mind freedom of supporting speculation hypothesis, and patience, so personal relational abilities. To what extent these qualities played a role over these 40 years that led you to this discovery?
Absolutely correct. This is something that's kind of research, which I haven't done that. I couldn't have possibly done that by myself. So many people have been involved. Hundreds of people have been involved. Young people who came up and wanted to do PhD studies, and they were involved, and then became famous on their own through this kind of research. Another thing, of course, is if you want to do experiments like this, you have to collaborate between institutions and nations. And I would say, I've told you one of the very wonderful examples of European collaboration, because the European Southern Observatory, when it started in the 1960s, was by far not competitive compared to the American colleagues and the big American telescopes at the time. Nowadays, I would say, with great pride, I would say the ESO is the best and biggest, most capable observatory in the world. And working with the ESO colleagues and everyone in Europe was the core of this experiment, very clearly.
Grazie.
Thank you. Another question I'd like to ask you. So you showed us this reality that seems so far away and distant from us. So black holes seem to be something far away from our lives. But still, even if they are so far away and distant from, our normal idea of a physical reality, actually, first of all, we realized that black holes exist, thanks to your study, and up to a point, we can somehow perceive the behavior and the nature. And it's quite surprising because, in the universe, we are a teeny-weeny point, so small. But still, from this little point, we can read and interpret and watch this faraway reality. There is the famous sentence by Albert Einstein. So the most incomprehensible thing about the universe is that the universe is comprehensible. So what do you think about this paradox, that the most incomprehensible thing is that it is comprehensible?
Yeah, I always feel that the fact that societies in modern society, but also in the classic periods, would invest in research is really one of the signs of human being and our curiosity to understand the universe. I always compare this to a walk in a forest which you don't know. So you enter this forest, you've never been there, and you're awed by the beauty of it. That's the beauty of the universe. And then you discover things. You discover flowers and blue ones and red ones, and these are the galaxies and whatever. And after a while, you begin to understand, oh, the blue flowers are always on the left side of the path, never on the right side. That's when you have to understand more than just observe. You have to have a theory. You have to begin to do physics. And it's this kind of path from awe about the beauty of the universe, about its richness, is what makes this all so interesting, and perhaps also why societies are willing to give us the resources. And for that, I thank them.
Grazie.
Thank you, Reinhard. I do believe that we really had a great privilege, and this journey was magical, and thanks to the gaze that you helped us cast on this world, shows to what extent the rigorous, accurate, refined study of data and scientific interpretations, I mean, is not opposed to the beauty that you were just mentioning now. It's like a new possibility of beauty. It's like a sort of letting into our horizon, our lifescape, something that promises us a beauty that otherwise would have remained distant. So our self is enriched. So we are enriched by and through this relation to everything in the universe. And so everything shows its unique beauty. A big, big thank you again for having been with us.
E speriamo naturalmente.
And of course, we hope very, very soon to have you here in person in Rimini.
Is that traveling is difficult these days. So,
Grazie.
Thank you. I'd like to say another couple of things. So the dialogue and conversation with Reinhard continues because tomorrow at 6:30 Italian time, we will have the opportunity to have a webinar that is going to be held in English. And so you can connect. And in the scientific area of the meeting, in the Eurisis campus, there is also going to be a translation into Italian. So do not hesitate to join the webinar there if you want to listen to the translation into Italian. And for those who would like to ask questions, please send an email to eurisis@org. So eurisis@eurisis.org. And we're going to have a physicist who is going to somehow read and select the questions. So see you tomorrow. And the meeting relies on our contribution to exist. So it is a gratuitous event. It is free of charge, so do not hesitate to donate at any Donate Now desk that are marked by the red heart, because this is thanks to these donations that the meeting can keep existing and offering these fantastic visions on reality. And again, this evening we had the privilege. And thank you again, Reinhard. Thank you.
Lui purtroppo non ci vede.
Unfortunately, you cannot see us. You cannot see the audience. Thank you very much indeed.